Hi everyone, I'm Roger Lu. I'm currently a PhD candidate in University of Waterloo and Perimeter Institute. So today I will introduce the YAO ecosystem, which is the open source software ecosystem that we have been developing since 2018 that aims to help the research in the field of quantum computing and quantum information. So what is quantum computing? So quantum computing has been an emerging field, and it has been made a lot of progress in recent years that has potential applications in chemistry, combinatorial optimization, cryptography, and machine learning. And most of the algorithms can be represented as a quantum circuit. So to set these algorithms, we need to think about, for example, how to simulate a quantum circuit and how to design the quantum circuit. Especially if we can manipulate circuits or differentiate the circuit. So we developed this software framework called YAO back in 2018 that aims to facilitate this type of research. So in this review paper in 2019, actually listed three framework that supports this type of applications, which is called versional quantum algorithms. So to give you some background, what is a versional quantum algorithm? It is about hybrid quantum device and classical resources. For example, we have a parameterized quantum circuit, and we can send the parameters back to the classical computer, and the classical computer will do the classical optimization on the parameters, so that eventually will optimize the output of your quantum circuit towards your to optimize your loss function. So we're one of the three frameworks that supports this functionality with automatic differentiation. And we're also the only open source project that is fully funded by academia. And our framework is built on the modern language called the Julia programming language. It is a fast, generic, and differentiable programming language. By fast, it means we can achieve performance on par with pure C programs. And also the programs are generic. Our simulators and the whole framework is generic, which means you can insert different kind of algebras of the primitive types. For example, the dual number type can give you can directly give you forward mode differentiation. The symbolic number can give you a symbolic calculation on the quantum circuit. Plus, this allows us to support GPU programming high-level language very easily. And the other very interesting and very useful feature is of differentiable programming, which has been applied in many scientific research areas. And there are two main AD engines in Julia, which is Einzam and Zygote. So Julia was originally invented by these four people in MIT Julia Lab. So if you want to know more about the Julia programming language, here's the paper of the original project. So YAO is built using the Julia programming language. It has all the feature that Julia provides. And the YAO's framework is built around the intermediate representation we call quantum block intermediate representation. So this intermediate, surrounding this intermediate representation, you can, for example, extracting the matrix operation from a quantum circuit, or executing your quantum circuits on GPU or a real quantum device, or on your CPU simulator. So on the right hand, we have a very detailed benchmark about the performance of simulating quantum circuits using using full amplitude methods among comparing with other frameworks. So you can see we're one of the frameworks that have the top performance compared to all other frameworks. So the team has been growing from 4 people initially, and with a few other people join later. And now we have some core developers inside this ecosystem from different institutes. So we kind of grow our ecosystem a bit more in the past 2 years. So, for example, we implement a quantum algorithm zoo package that it has a currently implementation of all quantum with a lot of quantum algorithms using the YAO.gl. This includes algorithms like a well-known algorithm like quantum versional quantum eigensolver, QoA, and Shor algorithm, Grover search, and many more. And we also developed a new compiler that aims to unleash Julia on quantum devices. So in order to run the quantum program on these new quantum devices, we need to do some compilation. So we have done the first pipeline that compiles OpenQASM 2 to Julia, native Julia, and then compile them to the YAO IR, which is SSA based, and then compile them to the IBM-Q or OpenQASM 2, or back to the OpenQASM 2. So we also implemented compiler optimization inside this compiler, which includes CX-based simplification and single Simon-based simplification. So this is one of the simplification projects that is called ZAX Calculus. So ZAX Calculus is a graphical language for quantum circuits. It makes certain kind of algebra such as Clifford algebra very simple to evaluate under this diagrammatic representation. So we implemented the algorithm in this paper using pure Julia that allows us to achieve a large speed up compared to the original Python implementation. So for some cases, we have the 60 times speed up. We are 60 times faster than the original Python-based rewriter. So this allows it to use, with plugging to the YAO compiler, this allows us to use the ZAX calculus to do circuit simplification. The other interesting project we have been working with inside the YAO ecosystem is the QON, which is another topological language for quantum information. This representation uses string null diagrams to represent quantum operators. This will make both Clifford algebra and match gates very easy to understand. However, for theorists, this diagrammatic representation is beautiful mathematically, but they're very hard to reason about manually because it can be quickly intractable when you have a lot of string nuts. So our contribution is to implement our automatic engine that help user to contract and visualize such string null diagram. And the other package is the YAO to Einstein package that converts the quantum circuits to tensor network-based simulation. So this implements the same algorithm has been simulating the Google Sacramento circuit, which was the claim of quantum advantage. And the other still work in progress project is the basic quantum circuit emulation subroutine that aims to automatically compile optimal loops for this quantum circuit or tensor network contraction intrinsics. So some of the intrinsics got even 100 times speed up compared to our current stable simulator. So besides these quantum circuit simulations, we also had a collaboration with Harvard and QEra Computing in the past 2 years with the rubric system and maximum independent set problem. So what is the maximum independent set problem? This is a very important combinatorial optimization problem that appears in many different fields. So an independent set is, by definition, are vertices as subsets of a graph that, and all the vertices are not connected. So, for example, on the left hand is independent. The blue nodes are one independent set. The maximum independent set is about finding the maximum independent size on a graph. And this problem naturally is embedded on a Ripper Hamiltonian. So we can solve this problem by finding the ground state of the Ripper Hamiltonian. And to facilitate the research around the Ripper system, we build this Ripper software development kit in collaboration with QRA and Harvard. That aims to simulate the dynamics of the Ripper system. It supports ODE solvers, Krylov solvers, and also with CUDA acceleration. Plus, it's also built on top of EL. Actually, it's built around the Ripper Hamiltonian symbolic expression, which is the same intermediate representation we use in EL. So here is a glance of what it looks like. So it has a high performance and accurate emulation for Ripper system, and also support. It currently has experimental support of automatic differentiation. And we also support blockade approximation, which allows us to simulate 8 by 8 number of qubits of the Ripper atom array. So this has been very helpful in our recent results on using the Ripper atom array to solve the maximum independent set problem, which appears on Science just recently. And it's built on the nice ecosystem, on top of nice ecosystem of differential equation, Julia GPU, and YAO. In the end, we also care about cloud servers, wrappers, and real connection with the hardware. So we currently have a client for IBM quantum services, experimental implementation for the AWS Bracket client. And in July, we're going to have a blockade schema that connects the Ripper machine from QRA computing. We also has been working with quite a few Summer of Code programs in the open source community, such as Google Summer of Code, Julia Summer of Code, and Open Source Motion Plan, Quantum Open Source Software Foundation. So on the left hand are the past projects we have been mentoring in the open source community, and some of them has been become a very popular package among the field. So in the last, thank you for your attention to our open source project. If you feel it's useful for you, please give us a star. And we'll list, this is a website, and we'll list the most important features of our software framework on the website. Okay.